So let's get started. Good evening, everyone. Thank you for joining us at the Spotify San Francisco office tonight for a meetup. I'm here to talk about playlist recommendations at Spotify. So I'll start with some information about how these are generated, and then dig deeper into how we use Scalding throughout our playlist recommendations feature to do some pretty amazing stuff. And then I'll sort of tell about. Oh, sorry. Now? Okay. Hi. Today I'm going to talk about playlist recommendations at Spotify. Initially, I'll talk about how these are generated, and then we'll dig deeper into how we use Scalding to do some pretty amazing stuff with this. So who am I? My name is Nikhil Tibrewal. It's pronounced as Nick Hill. And I'm a data engineer on the Lambda Squad. Lambda Squad is our team's name in New York. And we work on the most awesome machine learning features on Spotify. I graduated from Carnegie Mellon University in Pittsburgh in 2013. Got a bachelor's in computer science and an additional major in economics. Joined Spotify right after. I've been with them for a year and a half, and I've primarily worked on playlist recommendations in my time there. Just to give you a sense of Spotify numbers, Spotify started in 2006, and we're available in 58 markets right now. We have over 75 million active users. 20 million of those are paying subscribers. We have a catalog of over 30 million songs, 20,000 added every day. We have 1.5 billion plus playlists, and a terabyte of logs are logged every day, at least more than that, I believe. So this just gives you an idea of the kind of scale we're operating at and the kind of challenges we might face going forward and making Spotify more awesome. Just a quick overview on the kind of recommendations we offer right now. We have the good old Discover tab. It's been around for a while. And we have track, album, and artist recommendations on there. And we have radio. We have related artists, for example, this related artist for Ellie Goulding. And then we have Discover Weekly. This was launched a few weeks ago and has created quite a bit of buzz. And then something new that we've launched recently is playlist recommendations on something called a Now Strip. I'll tell you more about that in a couple minutes. But this is the newest feature that we've added where we're serving playlist recommendations. So what exactly is this Now Strip? Well, this Now Strip is essentially a list of music, human-curated playlists and shows for you right now. This is the kind of music and content that Spotify thinks is best for you at this very moment. And so along with this content of human-curated playlists that are created by editorial teams, we sprinkle through some different kinds of playlists that we believe are good for you according to your taste. So these are the recommended playlists. And these are sprinkled throughout the strip to tell you to give you sort of a machine learning based plus human created experience, because that's where we believe the real catch is. And this is available for some users. You may see it now, you may see it later on, but it's being rolled out. So now you're probably wondering how these playlist recommendations are really generated. Let's go into that next. So at the base level, the first thing that I want to note is that we only recommend human-curated playlists, and there's a few reasons for that. We have about 1,000 plus of these playlists, but the main reasons are that these playlists have really well-designed cover images that are depicting what kind of content is in there, sort of giving a user the sense of a really inviting playlist content in there. And then these playlists also have thorough descriptions that are describing what kind of genres are in there, when we think these playlists might be appropriate to listen to. And then a title that reflects what kind of content is in there as well. As an example, you can take this playlist that has a pretty nice image of people having fun on a Sunday, I think, and there's a title, and then the description is telling you what kind of music is in there. In this case, there's indie pop. But then the reason that we have to go through these playlists is that there's other kinds of playlists in that 1.5 billion that are like this one. The title here is literally shit, and the cover image is not telling you much about the playlist. It's a mosaic of 4 albums in there, but you can't really get much out of it. So we can't really recommend that to a user and be like, "This is your taste." They'll be like, "No, that's not my taste." So let's go next into this recommendations pipeline that is generating all these recommendations. The first step in this pipeline is the candidate generation. This is the part where we generate a list of candidates. Candidates are playlists for each user, and then we do more steps on that. So, but at the base level, there's this concept of generating track vectors that are generated from collaborative filtering and a few other models. But basically, these track vectors are sort of a representation of the kind of features that these tracks will have. And these are completely latent feature vectors, so we don't really know exactly what the features are. But this is how we represent each track in this n-dimensional vector. I can dig deeper more into that later off presentation, but we won't have time for that today. And that's not really the focus of this talk, but come grab me later if you want to know more about that. And then there's the concept of sort of vectorizing playlists. What this means is that playlist vectors are derived from track vectors. Tracks are the base content of a playlist, which is where we have the most information about a playlist. So you would sort of come up with a playlist vector that is derived from these track vectors. And then the next problem comes, if it loads. The next problem that you would like to solve is you would want to find playlists that are close to each other, right? So for that, we use something called ANOI. This stands for Approximate Nearest Neighbors OEA. The OEA part was added recently. Before that, it was something. It was created by Eric Bernardson, who used to work at Spotify as well. But basically, this stores these playlist vectors in an n-dimensional space using the Approximate Nearest Neighbors algorithm, through which you can query for closest playlists. But to query for closest playlists, you also need the user listening history, right? And that's where we use this concept of a user vector. Again, that is also derived using the user listening history from the tracks and other content that they've streamed. And in this case, you might be thinking that what do we do over time? Like, what about tracks that the user listened to a long time ago, many weeks ago? Well, those tracks we would weight less, because we would like you to get recommendations that are more or closer to something you've listened to more recently. So we would add some sort of a time decay to those tracks and give you more recent recommendations. And then there might also be a concept of users that are having different kinds of tastes. So let's say a user might be listening to metal and indie. These are completely different sort of genres, and if you combine them, there might be some discrepancy there. So there could be a concept of separating or generating two different vectors for a user based on that. And again, we won't dig deeper into that, but that could be done as well. So once you have these user vectors and playlist vectors that are generated in the same space, what that means is they're both generated at the base using the track vectors. You can use the user vector to query the playlist vector using the ANOI tree I just talked about. And the way you do that is just ANOI tree.getNearest. The seed vector here can be the user vector, and k can be the number of playlists that you're trying to get, the k closest playlists. So this part gives you the candidates for a user based on the nearest neighbors algorithm. But then what more can we do from these candidates to give you better recommendations? This is where the ranking model comes in, that uses a lot more data to rank these candidates and sort of surface the more appropriate recommendations to the top. For example, we would use the genre information between the users or between the user listening history and playlists to surface the playlists that are more closer. And this distinction is especially appropriate when you think about Chinese pop versus Korean pop. They're pretty close, but you would like Chinese pop to come up further for a Chinese person than Korean pop, or if that's the kind of music that they listen to. And then there's demographics data for realizing country and age groups, and then there's playlist popularity. As an example, take John, who is 21, lives in USA, likes rock music. His recommendations should compose of rock playlists that are popular in America and amongst 21-year-olds. Or so these should be the playlists that we believe should surface towards the top, and that's where this ranking model comes in. But then there might be the problem of this ranking model always ranking playlists in a certain pattern and the user getting the same playlist again and again. So we would add some sort of post-processing shuffling steps that avoid this repetition over multiple days and times. And just to give you a number of where we're operating today, we have 90% daily active users that have recs, and our efforts now are to improve these recs and get the next 10% that are probably the users who recently joined Spotify, so they don't have enough listening history for us to be able to get them recs. or the ones that have not been active for a while, and we're not able to get them something recent. So let's take a little step elsewhere to infrastructure and the kind of technologies we use in the recommendations pipelines to make it more robust and better. We use Luigi to manage the workflow. This was also something that was developed at Spotify by Eric Bernardson. And this takes care of dependency resolution, job scheduling, fault tolerance. So all of that is taken care of us, and all we have to worry about is writing jobs and just scheduling them once, and then Luigi will take care of all that. And our entire pipeline is written in Scalding. This is Twitter's framework, open source framework for writing MapReduce jobs in Scala. And this is something that I'll dig deeper into next. And then we run all our jobs on a Hadoop cluster composed of 1,200 plus nodes. It runs about 10,000 jobs a day. And then we have Cassandra as our primary backend storage that serves all these recs. And then just for playlist recs itself, we have about a dozen nodes. And at the very top, we have Java backend microservices that are serving these recommendations and doing the shuffling logic that I just spoke of. So Scalding, let's dig into that next and tell you how we're using that and what kind of problems we've had with that, how we've tried to solve them, and how it's benefited us. Scalding is comprised of a DSL that makes MapReduce computations look like Scala's collection API and is a wrapper for cascading to make it easy to define jobs, test, and data sources on an HDFS. Scalding with respect to playlist recs, we used to use Python back in the day before we switched to Scalding, and that posed a lot of problems. Primarily, our inputs and outputs were tab separated or in JSON format, and you can clearly see that that's probably not going to scale as the complexity of your jobs are going to go up. You'll have to keep track of your schema changes. You'll have to keep track of where the items are, and just catching errors early is just something that Python cannot give you. And then it's also hard to write tests because Python didn't really have a robust and strong testing framework for MapReduce jobs as Scalding does. So Scalding provided us with compile time error checks due to being written on top of Scala, and having that benefit of having type checking helped you catch errors early in terms of schema changes over time and just being able to manage those changes really easily. And then we also use Parquet and Avro for input and output. Neville, my colleague, will dig deeper into that next, or in the next presentation. But basically, Parquet and Avro made it really easy for us to be able to write these inputs and outputs. Something that we learned about Parquet as we started to shift over to that was that Parquet hurts performance when your data structures have really fat columns. So in the sense that they're very nested. The kind of data that you're trying to access is all the way deep. And an example for that is this data structure. It's a playlist, and at the bottom you can see it's an array of items. But let's say you wanted to access the added by attribute of each item. That's really deep in there, and that's really going to cause your job to use up a lot of memory. And it could happen that your job could just wait for a really long time, trying to get resources enough to do those queries. Something that Scalding has also helped us with is consistent data quality. When you write Hadoop jobs, you would like to write them once and be sure that over time, as these jobs run, your data quality stays consistent. And what we've been using for that is Hadoop Counters. We have wrappers in our internal Scalding library code that help us track flows and sort of count certain records in those flows and be sure that every day when this pipeline runs, we have the correct numbers. And as an example, you can see the way it's used is that you define the counter here. And whichever flow you're trying to count, you just increment the counter there. And in this case, this counter is counting the number of usernames that start with A. So at the end of the job, you would have this counter would basically contain the number of users that have a username that starts with A. And to extend that, what you can also do is you can add a verifying counter check at the bottom that verifies some sort of a min or max condition on the counters that you've added to your job, just to make sure that your job is actually doing, at least acting sane. And to even make that more robust, we've added a basically monitoring system on top of our counters, or using our existing monitoring system with counters, so that over time you can see what sort of a track your counters are taking, and adding monitoring alerts on that, so that if someday your counters take a sudden dip, you can sort of get alerts for that and act on it fast. Another thing that Scalding has really helped us tackle is pipeline tolerance. Job failures are pretty normal in Hadoop world, and it's really annoying with big jobs, especially jobs that are, let's take an example of a job that runs for 7 hours and it fails after 6 hours. Well, then you go and make a change, and you run the full job again. It runs for 6 hours again and fails again in the between the 6th and 7th hour. Well, that's a really, really tough job. And enter Scalding Checkpoints. What this helps you do is that it dumps an intermediate output of your job into HDFS, so that the next time when the job runs, that failed job runs, it'll start from that same checkpoint it placed. As an example, this job is using this checkpoint at this time. This is generating the user vectors, and the way you define the checkpoint is right here. You pipe that you put this pipe as a checkpoint, and you use the resulting pipe into your job that continues. And what's important to note is that these two parts, the checkpoint and the job that follows, happen parallelly. So you don't have to wait for this to complete and then have this part run. Something that is also important to note is that checkpoint itself is a map reduce job. It's more of a map than a reduce because it is just writing to disk, but it has the same caveats as a normal map reduce job where, because of cluster issues, it could happen that it's waiting for a while. And job runtimes are also something that everyone deals with. In the Hadoop world, they're trying to get their jobs to run faster and make sure that things finish faster. And the common solutions that we've always used were increasing the number of reducers or adding code optimizations. But you can only do that so far. At some point, you have to realize that there's other solutions as well. And the one solution that we're using is speculative execution. This is more of a setting in Hadoop where what this allows Hadoop to do is that Hadoop will track how many or how long each of your tasks is taking on average. And at some point, if it sees a task is taking more than average, it's going to spawn up a new task that is identical to that. And from then on, it's basically a race to finish. Whichever task finishes first, that output is used, and the other task is discarded, or basically killed. But this can also take up unnecessary resources because you are spawning duplicate tasks, and so you have to be wary of that. To use this sparingly, but for jobs that usually take really long. We've also been dealing with a lot with memory issues as we migrated from Python to Scalding. Back in Python world, we used to use something called Sparky. This was also developed at Spotify, and it's open source now. What Sparky is, it's basically a simple constant key value storage library for read-heavy systems with infrequent large bulk inserts. As you use these Sparky indices, you define them and they're replicated to all mappers so that you have quick access to this sort of a dictionary store to be able to look up things really fast. And usually our Sparkies were a couple gigabytes, but because of restriction in terms of machine memories, we couldn't really keep on using more and more memory in our Scalding jobs. So what happened was as our Scalding jobs required more memory, at some point we hit this memory limit that we couldn't reduce in the Scalding job. And the only way we could do that was get rid of the Sparky index. And then we realized that if you just do a join instead, well, it's not that bad. It takes up a little more time. You write less code, and it's just, it's a very, very, very small trade-off for some memory and some faster code. Another tool that we've been using is called Driven. This was developed by Cascading, and it's a sophisticated tool that collects telemetry data from running Scalding and Cascading jobs on a cluster and presenting them in an intriguing user interface. Let's see what that looks like. So that is the intriguing user interface. At the top, you have this Driven tool offers you this data visualization of your entire job. So it tells you what kind of sources are there, what kind of sinks are there, at which point there's a combine, at which point there's a flat map, which point there's a group by. And then once the job is executing, you can even see step-by-step breakdown of what's happening in there. What's happening at the map step, where the data is flowing. You can pinpoint bottlenecks. Like in the case of these two nodes, there was a really high read time. So you can sort of really understand what's going on in your job at a mapper and reducer level. And this has been really helpful in profiling our jobs. Some other awesome benefits that I think are worth mentioning about Scalding is that there's a pretty active community with some big players in there. And I think that really helps us developing in Scalding because we know that we can always rely on these developers in this community and we can contribute to it and learn more from that. For example, Scala itself has a library like NumPy called Scala Breeze that is pretty helpful in doing some strong linear algebra. And then something else also that is important to note is that data pipeline flows naturally follow the functional paradigm. So writing Scalding code is basically writing functional programming or specifically writing Scala code. As an example, let's look at this small job, which is getting track genres into the stream of all these users who stream tracks. At this point, you have a map, a group, both Scalding functions. At this point, you have map and group as well. This left join comes from Scalding. Sorry, these two are Scala. This is Scalding. So you can see it's basically writing Scala code with some Scalding sprinkled in there, which is really easy to pick up. And if you have some background in functional programming or Scalding, you're able to pick this up pretty easily. So what is the end result of using Scalding so efficiently? Well, it's productivity without sacrificing performance. Writing less code, spending less time creating and fixing errors, and working with an active community, that's like a lot more than you can probably ask for from any framework. And since we started using Scalding, it's helped us a lot. It's helped us be more productive without sacrificing any performance compared to what we were at Python. So that's been a pretty big step for us, and we've grown our Scalding repo as I think 10, 15 times since. So it's been a pretty big step that's been very, very helpful. And that is all I have for today. Do question and answer now? Any questions? Yeah.
How often you talked about two vectors, user vector and other
playlist vector.
Yeah. So how often the first one is actually getting updated, or is it actually being recalculated each time for each user?
No, so they're updated every time the track vector is updated. So everything relies on the track vectors at the base, which are generated every now and then whenever we have more data, whenever we have enough data. So
track vector update is actually independent of users interaction. Like it's actually updated for all.
Yes. Yeah. So all our recommendations will be using track vectors. Yeah.
Say you use Java for microservices and Scala for so what's the actually rationale like using Java for microservices and Scala for other tasks?
I think we also used to use Python as a microservices language back in the day, and then at some point we shifted to Java before we shifted to Scala. So the shift to Java happened before the shift to Scala happened. So then we just stuck with that. Yes?
Did you look at using Spark, and why did you not choose to use Spark?
So we didn't look into choosing Spark for playlist recs, but we are using Spark for other jobs that we think it was more appropriate for. In terms of playlist recommendations, Scalding was giving us pretty good performance. So at some point, we didn't. It was never a requirement for us to sort of start to look into an alternative when we are getting a really good performance with this, right? So. Yes.
Out of curiosity, you said 90% of the people do have recommendations. How many of them are using the feature? Is there any data on that?
I can't really release that yet, but that's.
Also, a quick follow-up. So for the other 10%, you said since the users are new or they might have they might not have recent history. Have you considered using their friends maybe as a point to say like, oh, their friends have been active and they are listening to this kind of music, maybe we could suggest this kind of music to these people as part of the recommendation algorithm? Yeah, I mean that's definitely been part of it, but the users who haven't been listening, then it becomes more of a problem of having them come to use Spotify. Okay. And that's a whole different problem, right? Okay. So we do need some streams from them to be able to get that data in, right? Cool. Thank you, guys.